Hello, AP Physics students. How are you? This is Dr. Bennett. I am sending you this video because during this week, as you know, we will not meet. Our AP Physics lab class will not meet. So in lieu of that, I'm going to have you guys do two virtual labs, and the first of which being, as you can see from the screen, is called the force table activity. So the link is there at the top, mrwaynesclass.com/vectors/force table underscore table, force underscore table / index.html. You see it there. I'm going to just highlight it there. Okay. But you will, of course, be sent the link. But the purpose of what we'll be doing here is to just kind of expand our understanding of forces and equilibrium. That's our next concept we will I'll have you guys explore through this activity. But we basically, I don't know if you guys remember, but for our last test, we actually had a bonus question that dealt with this very same thing. Basically, we had three vectors, and I was asking you to find the resultant vector, find the vector that will give you a resultant of 0. A resultant of 0, if we look down at this second picture here, you see how these three vectors are being added together? Well, the resultant is 0 because when we add them head to tail like this, we will get a resultant of 0. Now, what's kind of interesting is that if we look at this top picture, you see the three vectors here. If we add them together, the resultant is not 0, right? We have a non-zero resultant. That means that there is an unbalanced force that needs to be added. Well, what's cool is that you see how the red vector is a resultant. If we were to add the exact opposite of this vector to all three of these, we would get a 0 resultant. Okay, so let's kind of talk about this in a little different way. Okay, so this activity is called a force table. So let's take a look at a force table. Okay, and it looks like this. Okay, here we have 4 pulleys. Okay, 4 pulleys, and they all have a string attached to them as well as this center ring. And as you can see from the assembly, you have the weights that are hanging off of these. There are different weights, as you can see. Okay, this has maybe about 3 stacked up there. This has several more stacked up, perhaps larger masses. And so each of these mg's, right, this is a mass, and then of course gravitational force is pulling, gravitational acceleration is pulling down. So each of these is creating a force. Now the tension that's pulling on this is the same as the weight that's hanging off of it. So each of these represents 4 different forces. Now, what you probably can't see close up is the fact that they're all pulling on this middle ring. Okay, this middle ring, it is not touching this middle like brass dowel or a brass little pole that's kind of sticking out the middle. It's because all the forces, where they're oriented, their direction perfectly balances the ring. Okay, so let's take a closer look at the top view of this. Okay, so if we were to look straight on down, with the top view of this, if we notice, okay, this is 0 degrees, 10, 20, all the way around. This is 90, all the way around, 180, 270, and then back up to 360 or 0 degrees. Now, each of these strings, now keep in mind there's a force pulling on this from the weight of each of the masses. So this particular force is at a certain angle, and it looks like about 15 degrees for that one. And if we progress a little bit further, okay, this one is perhaps at 80 degrees. Okay, so some force at an orientation. Moving on around, here's another force, looks like at about 150 degrees, measured again from 0 all the way around, is some force at a direction, some tension, right, at a certain direction. And the same thing for this one. Now, if we can imagine that, let's say this fourth one is not there. Let's say if we just chopped it off and we just let it go. Wouldn't this ring hit this middle bar, this middle little dowel, a piece of brass sticking out? So if we remove this force, you guys, that would mean that these three forces, that the remaining forces would not be in equilibrium, meaning there's not a balance of forces. It's not a balance of forces. So this fourth force balances these other three, keeping them in equilibrium. Okay? All right? So that's the idea. We need to find out what fourth force that we need to add to counter or to balance these other three. Okay? All right, so here's what our simulation page will look like. Okay? It'll essentially be three forces at different orientations, and we must find the missing vector that would put these forces in equilibrium. Okay? So everyone will be given different forces, and over here is what we will need to look at. But actually type in your answer at the bottom in this kind of red box with the magnitude and the direction. Okay? All right, and that direction will be measured from the 0 all the way around. Normally we just have the acute angle in there, but they are looking for the angle as measured from 0. Okay? All right. Moving on a little bit further. Okay, so here again is your objective. Given three force vectors, calculate both the force, a fourth, see they spelled that wrong, a fourth force, such that when it is added to the three, all the forces will be in equilibrium. Okay, and you can actually check it in simulation. It'll tell you if it's right or wrong. Okay, so here you can read through the instructions again, but I pretty much described what you'll be doing. You will be using the component method and not a scaled drawing. Okay, you'll be using the component method, and we know what that is, our table of x and y's, right? Okay, so here's the simulation. You click on that and it will bring you to this lovely screen. Okay, so again, this explains and goes into more detail about what I just explained on the previous screen. All right, but let's go on to the simulation. Okay, so click on it, and here is my set of three vectors. Okay, now what I'm going to be doing for you guys is showing you how I want you to turn this in. Okay, you will be turning in a screenshot of the vectors that you get. So you can either I like doing a screenshot, which is, for my computer, it's like the function print screen. Okay, every computer has a print screen ability. So when you do a screen capture, I just need to see what forces you get. Okay, if you have trouble doing that, just draw this picture with your vectors on it. Okay, if you have trouble doing the print screen and then cropping it out, then just write these vectors down, just this picture right here. Okay, all right, so here's what you do. All right, so here's this cool little tool, right? It can actually tell you what angle these vectors are, and as you can see over here, angle tools measurement in degrees, and that's always measured from the 0 degrees right here. So you go up, you're like, oh, okay, the magnitude of this one is 123.1 newtons at 76 degrees. Okay, so I'm going to go over here and type in Word. I'm pulling up my Word document, but you can of course write this inside of your lab book. So what is that? 123.1. Okay, 123.1, and it is at 76 degrees. I think that's what it said. Yeah, 76 degrees. So write that in. And of course the x component, right? Both x and y components would be positive. So 123.1 cosine 76. And then the y component will also be positive, 123.1 sine 76. Okay, and I'll calculate all this stuff out once I have all my vectors. Okay, all right, so I'm going to go back over here and look at my next one. Okay, now this next vector, wow, that one is kind of nice. That's perfectly at 180 degrees. And guess what, guys? This only has which component, x or y? It only has an x component. So this would be just plain on negative 142.3 in the x direction and 0 in the y. Okay, so let me go back over here, 142.3. So my vector is 142.3 at 180 degrees. And so that whole thing is just going to be negative 142.3 and 0 for y. All right. Okay. Next vector. All right, so this thing over here, okay, you see my angle, it still measures from the positive direction into the counterclockwise. So all the way around this thing is 322. Now, let me get the acute angle for that. Minus, okay, so I'm just going to do 360 minus 322, so that's 38 degrees from here. So this one is going to have a positive x component and a negative y component. Okay, so 372.9, go back over here, 372.9, and what do we say, at 38 degrees. All right, positive x component, 372.9 cosine 38. Okay, and then a negative y component, so I'm going to go ahead and put that in there, negative 379, I'm sorry, 372.9. All right, sine 38. All right, so type that resultant word in there for us. And so I'm going to get all these numbers, add them up. So this will be my r sub x component, and then this will be my r sub y component. Okay, just put a little x there as a capital. Okay, all right, there we go, better. Okay, so we're going to add all this up. Now once you do that, is this what we put in there? No, this is just the resultant. We need to get the exact equal and opposite number, whatever we get right here for Rx. Okay, highlight that in yellow. Okay, so I'm going to get this number and we have to get the opposite of it. Let me create another thing below here, because that is the number that will give us the force that will counter. Again, we're balancing, so we need something to counter what's going on with these three things and get the opposite. So whatever number I get right here, I'm just going to get the opposite of it. Okay, oops, did that wrong. Okay, and then whatever number I get right here for r sub y, I'm going to get the opposite of that. Okay, then I'm going to take both of these, take the square of the square root. I'm sorry, the square root of the sum of the squares. That's probably a better way to say it. And that will be my magnitude that I put here. But make sure you get the opposite after you add all of your components together, because we want to counteract those numbers. Okay, and then do the tan inverse of this one divided by this one. Okay, and that's what you enter into here, magnitude, the mag and the dir, right? Then click your check your answer. I know you're going to wait till after to do that. Oh, it's wrong because I didn't enter anything. Okay, So you always get another chance. It'll tell you if it's right or wrong. So you can't go in, all right? You got to make sure you enter the right one. Okay, that's the first one. Click for new vectors. Oh, this will erase my current vectors. Okay, fine, because I'm ready to go on to number 2. So you do the same deal, right? Each vector, get the X and Y components. One trick I'll tell you is that for our vectors, just like over here, we subtracted 360. 360 from, for this case, will be 325, and you'll get this acute angle. You can do the same for over here. All right, this is 131. You can subtract that from 90. You can use this upper angle here, acute angle, or use this one, 180 minus, right in the center, 131. So the option is yours. All right, but show your work, guys. Show me what vectors you have initially, and get that force that will balance or put all forces in equilibrium. Everything is perfectly balanced, okay? All right, hope that was helpful. Let me know if you have any questions, and we'll see you real soon. All right, thanks, guys.